Welcome back, my friends. Today, we are taking some notes on chapters 12 and 14 from your textbook about gravity and orbits. For this one, you will need your science notebook, your physics everything sheet. It's on the back of your core tools packet, physics everything sheet, and your physics textbook opened up to page 168. 168, chapter 12. So three things: textbook, physics everything sheet, notebook. It is a triple hitter today. All right. So let's start on page 168 with chapter 12. So chapter 12, sections 12.1 through 12.3 are all talking about the gravitational attraction between the moon and the Earth. The question being, is the moon falling towards the Earth? If it is, that could be concerning because the moon is large and massive, and if it hits us, that would be a big bad for the Earth. So is the moon falling towards the Earth? Well, it turns out that we know that gravity is pulling it towards the Earth, and if it's accelerating towards the Earth at 9.8 meters per second squared or whatever rate, then it would be being pulled towards the Earth. So why doesn't the moon hit the Earth? Turns out the moon is in fact falling towards the Earth right here, but it's also moving sideways. And since it's moving sideways, it moves sideways and then gets pulled a little bit towards the Earth. It moves sideways and then gets pulled a little bit towards the Earth. And so it ends up looking kind of like something like this, where it goes sideways and then at the same time gets pulled towards the Earth. It goes sideways and then gets pulled towards the Earth, and it just kind of stays in orbit the entire time. So its tangential velocity, its velocity moving at a tangent, is great enough so that it is always falling to the Earth, but never getting any closer because the Earth is round. So by the time I get to one place, I'm now further around the Earth because of its rounded shape. Okay, the second question there is the moon is the Earth falling towards the sun? And again, the answer is yeah. The Earth is constantly falling into the sun, but never actually getting any closer. I mean, it gets a little bit closer during certain months. January, we are slightly closer because of our elliptical orbit. July, we're slightly further away. But on the whole, we stay in orbit the entire time because of that tangential velocity. So I've drawn in red the tangential velocity. The tangential velocity means it's at a tangent. So it's a line that would hit this circle at just one location where it is right now and then goes out in a straight line. And the pull of gravity would be towards the center of that circle. So that would be towards the Earth in the moon's case, or towards the sun in the Earth's case. And those two things kind of balance each other out so that it always stays on this blue orbital path. All right, now let's pull out your physics everything sheet because we are ready to add another line to your physics everything sheet. And the line that we're going to add is Newton's law of universal gravitation. So we're going to call this F sub g. The variable is a force of gravity. The concept is the force of universal gravitation. So the concept is the force of universal gravitation. We're using the variable F sub g. So what is the force of universal gravitation? The force of universal gravitation is the idea that every object is attracted to every other object in the universe directly proportionally to their masses and inversely proportional to the distance between them squared. So if you want things to be more gravitationally attracted, make one of them bigger in terms of mass, or bring them closer together. So the radius, the distance between them, will make a big difference, and the mass of each object makes a big difference. More mass means more attraction. Closer together means more attraction. Okay. We can put that into an equation. And the way that we can put it into an equation is like this. Our equation is right here. It's that F sub g is equal to big G, which is going to stand for the gravitational constant, times mass 1 times mass 2 divided by the distance between the two objects squared. So big G m1 m2 over d squared. Sometimes you'll see this d represented with r instead, r being the radius, which is just, again, the distance between two masses. The unit for the force of gravity is newtons. It's a force, right? So the universal gravitation force is newtons. And then in terms of notes, let's detail out a few things that we know. So first, we're introducing this new constant, big G. It's called the gravitational constant. And big G, the gravitational constant, is a really, 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 really small value. It's 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. If I were drawing that out with a decimal point, it would be 0.0000. You can read the zeros. It's a lot of zeros. 667 at the end. So it's a very, very, very small amount. Remember, for scientific notation, something times 10 to the negative 11th means move the decimal point 11 times in the small direction. So that'd be 1, 2, et cetera, 11 times. If it's times 10 to the positive number, then I would move the decimal point over that way, and that's how you get into the thousands or the millions or the billions or the trillions. To the negative is to like the trillionths. Okay, so that is the line that you should have added for your force of gravity, force of universal gravitation. Flipping on to page 175. So we're now on page 175. And it introduces this idea of the inverse square law. So gravity is something that is inversely squared to distance. So as you get further and further away, you get less and less force of gravity, and it's squared. One way that the textbook conceptualizes this is thinking of a butter gun, and the butter gun sprays out butter at a certain angle. So if you are just one distance away, a distance away of d, you spray out and just get 1 square's worth of butter, and it would be 1 millimeter thick. If you're 2 distances away, then this would be 1 over the distance squared. So 2 squared is 4. So it would be 1/4 of a millimeter thick, but it would be spread over 4 boxes, 4 squares. If you're 3 distances away, 1 over distance cubed. Nope, it's still 1 over distance squared. Sorry, it's 1 over distance squared, but the distance in this case is 1 over 3 squared. Okay, so in this case, it was 1 over 2 squared. In this case, it was 1 over 1 squared. And instead of being 1/4 thick, that should read 1/9 thick. So it is 1/9 of a millimeter thick, because it's going over 9 squares. So I'm taking the same amount of butter, spreading it out over 9 times more area, so it'll be 1/9 as thick. So this is the same idea kind of for gravity, where the further away you're getting, the more that gravitational pull is being spread out. It's also the same for like how light and heat comes from the sun. The further away you are, you're getting a smaller percentage of the sun's light and heat, because it's spreading out in 3 dimensions, or in 2 dimensions, really. Yeah. The outwardness plus the 2-dimensionality of the surface. So that's the inverse square law. As you get further away, you're spreading out over a greater area. Okay, let's zip forward, and we're going to move on to chapter 14 about satellites on page 199. So if you flip on to page 199, looks like this, satellite motion. Okay. So let's take a look at satellite motion, chapter 14. So we start by discussing in here, how would you actually get an object to orbit around the Earth? And it gives this nice example of a girl dropping a ball and then throwing the ball and then throwing the ball a little bit harder. And it's talking about, is there ever a speed where you could throw the ball hard enough that it would go all the way around the Earth and come back and hit you in the back of the head? And assuming no air resistance, and no mountains or hills or fences or trees or any other object that would get in the way, yes, there is a speed that you could do that. And we can actually calculate that speed, and we can do that by looking at the curvature of the Earth. So the curvature of the Earth is such that if for every 8,000 meters you travel horizontally, you have 5 meters of vertical distance. And actually this 5 meters should be drawn there, right? That way is 5 meters. So every 8,000 meters sideways, you have 5 meters of vertical drop. And there are 4.9 meters of vertical drop. And it turns out that it takes 1 second for an object to fall 4.9 meters due to the acceleration due to gravity. So if an object falls 4.9 or 5 meters in a second, that means the object needs to travel 8,000 meters or 8 kilometers in that second. So the orbital speed for close orbit around the Earth is 8 kilometers per second or 8,000 meters per second, which is about equal to 18,000 miles per hour. Now, this has to happen outside of the atmosphere, because if it was inside the atmosphere, you'd have air resistance, and that would slow the object down and make it hit the ground. So it has to be outside the atmosphere so that there's no air resistance, and then the satellite can move smoothly, and it will orbit around the Earth. So that means every satellite that we put out into space, we have to send it up out of the atmosphere, and then we have to send it sideways at 18,000 miles an hour so that it keeps orbiting all the way around the Earth. All right. Flipping forwards to page 202. 202, we start talking about circular orbits and elliptical orbits. So far we've been assuming that everything is a circular orbit. However, in reality, most of the orbits are slightly elliptical. So if we exaggerate that a little bit, here's a circular orbit. And in a circular orbit, the object is always the same distance from the Earth, right? This satellite is, and a satellite is just a word for anything that orbits around a planet. So the moon is a satellite of the Earth. We have our human-made artificial satellites, and then we also have natural satellites like the moon and maybe some asteroids, just stuff that's floating around the Earth, not floating, orbiting around the Earth. So if an object is always the same distance from the Earth, then potential energy, since potential energy is equal to the mass times the acceleration due to gravity times the height, well, the mass is the same, the acceleration due to gravity is the same, and the height, if it's the same distance every time, this distance from here out to there is a height off the ground. Actually, it's a height from the center of the planet, but same, well, kind of the same. Then the potential energy would be the same all the time. Since the potential energy is the same, and my total energy has to stay the same, the kinetic energy or the speed of the object would also be the same all the way around a circular orbit. So around this circular orbit, I have the same potential energy and the same kinetic energy at all points. Now that's not true if I make it an elliptical orbit. So if I make an elliptical orbit, now my planet is down here in the bottom, and I've marked a few spots. I got A, B, C, and D, and these are 4 locations around my elliptical orbit. So if I get further away, now my height is greater, right? So let me do that blue line for you again. That is going to be my biggest height. So that's going to have the most potential energy. These ones are going to be like medium heights, medium distances. So those are going to have medium potential energy. And then this one, where it's closest to the planet, is going to be the smallest height. And so that's going to be the smallest potential energy, right? Now, since the potential and the kinetic have to balance off each other, these medium ones are going to have what we'll call an equal amount of potential and kinetic energy. Potential and kinetic energy. Over here, when I have lots and lots of potential, that means I'm going to have really, really small kinetic energy, big potential, very small kinetic. And over here, where I have really small potential, I'd have to have really big kinetic energy because the total energy needs to stay the same around the entire orbit. So that means the object is going to go the fastest as it's closest to the planet. It's going to go the slowest when it's furthest from the planet. So it'll be accelerating, 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 and then decelerating, 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 going slower, 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 slowest, all the way up at the top here. And then speeding up, 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 and fastest, and then slowing down again. Okay, so super slow at the top. It's not a top. This would be like a bird's eye view of a horizontal orbit. Cool. So where would the object have the greatest speed? It'll have the greatest speed closest to the planet because of that potential kinetic balance. Where is it going to have the lowest speed? It'll have the lowest speed furthest from the planet up here at point C. Okay. So that takes us through 14.4. Now let's talk a little bit about escape speed. So escape speed is how fast would something have to go in order to leave the surface of a planet. Now that's leave the surface just as one starting speed. The way that most rockets and spaceships leave the surface is that they exert force for a long period of time. They might run their engines for like 6 minutes or 8 minutes. So they're firing the engines and that's a constant force. So it's like accelerating, 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 pushing itself out, 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 out into orbit. But if you just had like one big slingshot, say, and you wanted to send an object into orbit or off Earth's surface and it won't fall back down at you, and you could only have a slingshot, so it only sends it once, the escape speed is how fast that would need to be. For the Earth, the escape speed would be 11.2 kilometers per second. That's 11,000 meters per second, or about 6.95 miles per second. So really, really fast, 21,000, 24,000 miles per hour. So you'd have to send it crazy fast. And so that's why our rockets don't just get slingshotted out, because we can't put them at that fast. Instead, they fire their rockets for a consistent period of time to keep accelerating, 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 and get out into orbit. And then if you look on page 208, there is a table that shows the escape speed based on the mass and the radius for some other planets. All right. So that explains a little bit about gravity and a little bit about orbits. Now you are going to do some practice problems. Chapter 12, those problems, and chapter 14, those problems. And then I'm going to have you, actually right now, we're going to go through and do a little math refresh, but I'm going to do it in part 2 of this video.